video we'll be discussing about the Hubble's law and calculation of the age of universe, which is nothing but we all know that universe is expanding and it is being redshifted. So yeah, using that particular information we will be calculating the age of universe. So we'll be using the same software video for this particular experiment as well. So we'll just log in, click on file, go to the file, run exercise. Hubble redshift distance relation is what we'll be using in this particular experiment. Click on telescope, optical. Here we are using optical telescope, and for this particular experiment we will be using the largest available telescope in this software, that is 4-meter telescope. Click on it, open the dome so that you can get access to the control panel of the telescope. As soon as this window pops up, click on the tracking, and here click on slew so that you will get a list of galaxies in this. And you can click in on any of the galaxies which are available here. You can just click on them and the telescope would slew to that particular coordinate, and yeah, we can find out the galaxy available in that particular cluster. So yeah, we are in this location. Now turn on the telescope. So as you can see, once the telescope is switched, and you can see number of galaxies present here, like there are so plenty of galaxies. You can click any of the galaxy available over there, and this is already aligned to a galaxy, so I'll just take it, get the access of it. The same thing what you did for spectral classification, here also you should ensure that the signal to noise ratio is above 50 and photon count is above 40,000, and note down the object name so that you can just mention it over here. Just a second, you can mention it over here. Here they are given galaxy, but this is also a galaxy, but this is not the common name given to a galaxy, it's the scientific name or astronomical name given to a galaxy. If you are lucky enough that if you get a clear software, then you might get the name of the galaxy in this manner, or you have to go in this way itself. So it doesn't matter, it's just a name. And click on go. Ensure the signal to noise ratio is above 50 and photon count is above 40,000. So as soon as the limit crosses, you can just click on stop, save the spectrum which you have collected, and yeah, in this collected data you have to find out the K line wavelength and the H wavelength. That can be done through this option. Go to window, observatory main control, click on tools, spectrum measuring, open the existing spectrum which you just saved. The file what I saved right now is this one, and just click on it. Okay, this is the spectrum which I saved right now, and this particular line or this particular spectrum is the K line. K line is always to the left and it comes first in the line spectra. So the K line wavelength should be noted here in this particular column, and the next one is the hydrogen line, that is H line wavelength. It's always right to the K line, and that particular wavelength is also noted. Okay, so these two wavelengths are noted. After that, in this same cluster or in this same field, go to another galaxy which is close by. You can go to any galaxies, but it should be in the same field itself. Okay, so come to this and get the access of it. Repeat the same thing. Note the name. So save the spectrum and repeat the same thing. Okay, you can directly go to tools, spectrum measuring, open file, load save spectrum, and this is the spectrum what we saved right now. Open it. Okay, this is the spectrum what we got. You can click on this point. This is the K line, and note down the wavelength here for the K line and H line value here. Okay, so after writing them down, this is the set of galaxies what you take in this particular field. Okay, in this field of galaxies, these are two galaxies what you have chosen. After this, click on slew again, go to observation hotlist, view, go to another field of galaxies. You can take any of these, it doesn't matter. I will take this one. As you can see, the telescope is slewing to the particular coordinate. So once you are at this point, you can go to any of the galaxies here. It's already aligned to a galaxy. It looks very dim, so preferably don't go to these these such objects, or the objects which are really very dim. So I think I can choose any other galaxy and just click on it. Okay, and it's not that you will get wrong readings or it is wrong to choose the dimmer ones, but the thing is, when we take the spectrum of such galaxies, it takes a lot of time to obtain a signal to noise ratio of 50, and even getting the signal to noise ratio to 50 is also won't be enough to get a proper accurate reading for such galaxies. So preferably don't go for such galaxies. Okay, here also we are getting almost the same thing, but it's fine. You can go with this. There is a galaxy over here, so get the axis, note down the object name, get the signal to noise ratios to above 50, and photon count should be above 40k. Repeat the same thing what we did for the first two cases. Just note down those values, and how much is the wavelength shifted, that is the redshift and K redshift and H redshift is calculated using this particular formula. That is, they have given the lab wavelength value and the wavelength of H line, So you will be subtracting this value with this particular number, so that you will get the value of the redshift. So in both the cases, these two are like the general values, and you will be subtracting the k value to the corresponding lab wavelength k line, and h wavelength will be subtracted to the lab wavelength h line, and you will get these values. Need not to be same for each and every case. It can be any value. It depends on the wavelength what I have obtained here. So as we can see, we have found out the values of k and h redshift. So to the corresponding redshift value, we will be able to find out the velocity from k line and the velocity of h line. So to calculate the velocity from k line into velocity from h line, we can use this formula which is given to us, that is v by c equals to delta lambda by lambda. This delta lambda is nothing but the value of redshift of the corresponding wavelength of the corresponding spectral line, that is k line, and the other lambda value, that is the normal lambda value, is the wavelength of the spectral line in the laboratory, that is this value. So in this case, the formula is basically 200 divided by 3933, that is 3933 Armstrong into speed of light. That is, we should not forget to multiply c to this particular term, and hence we will get this value if we calculate them. If we substitute these values and calculate it, we will get these value in some order, and the same goes for the h line as well. So average velocity is just the average of these two velocities, that is 1520 and 1507. Add them and just divide it by 2, you will get the value. So only for getting these two values we will be using the software. Rest all other things is calculation. Okay, so once we have got all the necessary readings or the observations, we can just focus on the calculation part. So after correcting all these information, we have calculated the average velocity, and now the important part is the finding distance, right? So here they have given field name and galaxy name as well. Galaxy name is nothing but what you have written over here. Field name, that is if you are lucky enough, like if you really get a software like CLIA which is purely for Hubble redshift itself, then you will have the option, or you will have a pop-up window which would display the name of the field, or else you can just ignore this field name and you can just directly go with the galaxy name itself. So draw another column of velocity, that is the velocity values whatever you have calculated over here should be mentioned in this part, and apparent magnitude is calculated in the spectrometer, that is as you have done in the spectral classification. There you get the apparent magnitude in the spectrometer, right? Here if there is an object name, there will be apparent magnitude right next to it. So from there you should remember to take down or note down the values of the corresponding galaxies. So after that, using the formula, that is distance formula, you have to find out the value of d, that is in parsec. Okay, so you can use the formula which is given here, that is, we know this formula, small m minus capital M plus phi by phi is equals to log 10d. Here the absolute magnitude m for all the galaxies is minus 22. Okay, so you should remember the formula. It will be written on the board, so chill. So after that, the small m value is noted down right next to the object name, and right substitute those values, calculate them, and as soon as you get the value of D, just note it down in this part. Here you just note it down, and I think you should be able to easily convert the parsec distance to megaparsec distance. It's not a big issue. You can just multiply the number, and megaparsec to megaparsec you can just I think you can just divide it. That is 10 power 8 divided by 10 power 6 would just convert that to the megaparsec distance, and you'll get the value 0.724. For the corresponding galaxy name and for the corresponding velocities, you will get certain distances. So after that you have to plot the graph. The graph would look just like this. So here you will be plotting the points in x-axis as they have given here. In x-axis it is distance, which is in MPC, and velocity, that is kilometer per second. You will be plotting the galaxies, and you will get a straight line just like this, and you have to draw a slope and find out the slope, that is h0, and this h0 is also called as Hubble's constant. So you have the slope would give the Hubble's constant value, and we know that Hubble's constant value would help us to find out the age of universe. So once you calculate the value of Hubble constant, the reciprocal of the Hubble's constant would give you the age of universe. So that is 1 divided by 70 km per second per MPC would give you the age of universe, and it should be approximately equal to 14 billion or 13 point, it should be in that range, that is 13.7 to 14 would be almost an accurate value, but not really the correct value. If it is even close, that's fine. So this is all about this particular experiment.